Okay, so welcome back to the next class of linear vector space. So first let me write what I find in my last class, that E1, E2, En, if these are the bases, then they are following few important properties. One is they are orthonormal. If they are orthonormal bases, then mathematically this is the first property. Second property, this quantity which I say the projection operator is this is called completeness. And finally, this is the matrix element. So first one is orthonormal, second is completeness, and third is matrix element. So these three properties the bases hold, and this is very important to note. Okay, that was my last class. So now in today's class we will try to understand few important aspects which is called change of basis or transformation of basis. Transformation of basis. We know what is basis. Now we need to find out what happened when the basis is transformed. Let me explain that in a more clear way. Before that, so say E1, E2, En are bases forming a basis in n-dimensional vector space. So they are forming a basis in n-dimensional vector space, ND vector space. When they are forming the basis in n-dimensional vector space, that eventually means that any vector x can be represented in terms of these bases. Fine, no problem with that. So I have a basis, and what I am trying to find out, a vector is decomposed into this basis where these are the components, these are the components. Now the question is this representation unique? Is this unique? Is this unique representation? Is this a unique representation? The question is a unique representation? That means, is it possible to write these things like this? That means I am writing the same vector using the same basis, but I am now changing the components. Is it really possible? That is the question. And the answer is no. When I am having a basis in my hand, I can able to represent this vector uniquely, and these components are unique. There will be no other component, and this component if I try to write, it will not be possible. So let me do that in a more convincing way. So say this is my equation 1, I can write the same vector with this is my equation 2. If I subtract equation 1 minus equation 2, if I subtract equation 1 and equation 2, then my left hand side will be 0. What will be my right hand side? Right hand side will be x1 minus x1 prime E1 plus x2 minus x2 prime E2 plus xn minus xn prime En. I will have the expression like this. Now, this is the component, that means this is a scalar quantity. I can write this scalar quantity in this way. So on. When C1 is x1 minus x1 prime, left hand side is 0. Now, you should remember this expression. This is a very important expression. This is a linear combination. This is a linear combination of the vector E1, E2, E3, En. The linear combination. And now, E1, E2 are bases. So, that means E1, E2, E3, En, these are linear set of linearly independent vectors. Now, if I have a equation with the linearly independent vector like this form, then the only solution that is possible is C1 is equal to C2 is equal to Cn is equal to 0. If C1, C2, C2, C3, Cn is equal to 0, then only we can have this equation to be satisfied. If this is 0, then readily I find that x1 is equal to x1 prime, x2 is equal to x2 prime, and so on. That means I can't write a vector when a basis is given to me with another components. So, the components are unique. You can prove that the components are unique when we are not using any other set of bases. So, first thing we learned that when a basis is given to you, I can expand a vector, and this vector can be represented uniquely for that basis only. Now, it is not necessarily that you will have only one basis in a dimensional vector space, there should be another basis also. So, let me give you one example. So, this is my preferred basis, natural basis. Normally, I took this natural basis in this way, E1 and E2 perpendicular to each other, and along this and this direction which is perpendicular to each other. Now, I am taking another basis which is also perpendicular to each other. This is my E1 prime and this is my E2 prime. These two are another basis in 2D. Mind it, this is for 2D. For 2D, I can take these two different bases. Now, if a vector is given to you, this is a vector, the general vector x is given. So, I can represent this vector either this component or this component. So, same vector is still same. I can represent the vector according to the choice of the basis. For example, here I can write this, take a projection here, take a projection here, normally the process we use, and then this vector will be represented in terms of E1 and E2. If I write this vector x, say my component is x1 which is this one, my component is x2 which is this one. So, I can write it this way. But also I can write this vector for this basis. This component, say it is my x1 prime, this component say x2 prime. If I do that, then the same vector I can write in prime form. This prime form. So, that means if a vector is given to me, that when I represent a vector, I can represent a vector according to my likings, and this likings is totally depends on how I choose my basis. If this is my natural basis, I can readily write my vector. If this is not a natural basis, it is different basis, but still it is a basis, then this component will going to change. In this particular class, we need to find out how these things happen. I mean, how I can find out these components in a different basis. If I change the basis, how this component I am going to figure out, that we need to learn. So, before that, let me go back to some basics which is also required here. So, some simple matrix relationship or matrix notations which is useful here. For example, a matrix X A is represented by this 1 1, say n by n matrix, make it simple, 1 2 1 3 1 n, then A 2 1 A 2 n, and then n 1 n n. So, the general component is A I j. The general component of this matrix is A I j. If I transpose this matrix, what is the meaning of transposing? If I transpose this matrix, that means my, say when I transpose this matrix, this component, I write it as another vector B. So, my B, this is B 1 1, B 1 2, B 1 3, B 1 n as usual, B 2 1, B 2 n as usual, B n 1 to B n n. But since it is a transpose of this is nothing but the transpose of this quantity. So, A 1 1, A 1 2, A 1 n, A 2 1, A 2 2, A 2 n, A n 1, A n n. The general component of this matrix is B I j, no problem with that, which is basically equal to A j I, because now it is changing. So, A transpose, if I make A transpose of A, then eventually what I am doing, that I am interchanging that, I am just interchanging that. This is one important aspect, that not a very trivial thing, but still you need to remember that I am just changing that. That is first. Second thing is what is the matrix multiplication? Say A B are two matrices. When I multiply this A and B, the general component I j, the general component of this matrix is represented by A I k B k j. I k is a dummy index running from say 1 to n if it is a n by n matrix. So, here one important thing you need to note, that the position of k, a valid matrix multiplication can possible when these two k are sitting in this order. So, order is important. So, order order is something which is important in matrix multiplication or valid matrix multiplication. When I try to multiply two components, so this k and this k should be sitting side by side so that they can be multiplied with this notation. This is another important thing you need to note. Apart from that, there are some matrix relation. For example, A transpose, if I make a transpose of this quantity, it will give me the same matrix A. This is a property of transpose which is also important. Then A plus B, two matrix A and B, when I make a transpose, it is same as A transpose plus B transpose. Third is the multiplication, A B whole transpose. If I want to make this, it is B transpose A transpose. Few things also need to know regarding the matrix, which is if A transpose is equal to A, we call this matrix symmetric matrix. If A transpose is equal to minus A, we call this antisymmetric or skew symmetric matrix. Now, whatever any matrix, if I multiply it with another matrix which is A transpose, this matrix is automatically a symmetric matrix. Why? This is say B, this A transpose matrix, I say this is another matrix B. So, when I make A transpose whole transpose, it will come like A transpose whole transpose A transpose, which is A transpose. So, this is my B transpose. What I am getting is nothing but B. So, B transpose B, that means A transpose, whatever the matrix I am taking, is a symmetric matrix always. Well, after having a very brief idea of what is symmetric matrix, how the transpose is working, because transpose is important in transformation of basis. So, let us go back to our problem, our original problem, transformation, basis transformation. So, this is the basis that is given. I want to find out for another basis, this is one basis and this is another set of basis, say. This is another set of basis. This is one basis, this is another set of basis. If two bases are given, then how to find out the components from this basis to this basis, that is the thing I need to do. So, my vector x can be represented in this basis like xi ei, I tends to 1 to n. In a similar way, I can write it that this vector can also be represented as this. I am just changing this component. This is dummy index, so I can change that. So, I need to put a prime here, sorry. So, one vector is represented in this, same vector can be represented in this. Now, what I am doing, my E1 vector, this is also a vector in the vector space, and when the vector space is there, I can write this vector in terms of the other basis also. If I write, then let me write the vector like 1 1 E1 prime, these are the components 1 2 E2 prime T 1n En prime. I can write a vector E1 in terms of other vector where these are the components of this, that I always do T1 T2 T. In the same way I can write E2 as E2 1 E1 plus E22 E2 prime. Left hand side all these things will be prime, and so on. En will be T in 1 E1 prime T in 2 E2 prime T in n En prime. So, I can find a general matrix form for that, for E. So, this T is nothing but the matrix T11, T12, T1n, T21, T2n, and Tn1, Tnn. This is a matrix. In my matrix I have, and my EI can be represented in general. EI can be represented in general summation of T j I E j prime, where j runs from 1 to n. From this expression I can write the general form. So, for example, E2 T2 T2 T2. So, this let me check whether I am doing. So, no, here should be I j. So, any E vector E1, E2 or E3 can be represented in in form of the matrix like this. Now, what I will do, that if this is known, I will just replace these things here. I just replace these things here. So, my x, so this I am going to replace. EI, I will replace this quantity. This, and the right hand side is already there. So, this I can rearrange slightly. Say j is equal to, I can shift this summation sign, bring this summation sign here, and then I put this summation sign I here 1 to n, then T I j x I bracket E j prime, which is fine. So, left hand side and right hand side, if I compare the component of E j prime and E j prime, I can figure out. So, component is now in my hand. So, let me, the component is in my form. So, x prime j is nothing but summation of I 1 to n summation of I 1 to n. Let me check once again if it is. Let me check once again everything is correct or not, then I go to the next thing. Summation of I T I j E j prime, I just replace this and Tij, I just replace here, okay, Eij is there. So let me put it here in this form, and then let us try to find out how the things is going on. Tij xi, this is the thing, summation of these things, this. Now one thing you should note here, which is important, that it is over some I which is running from 1 to n, Tij is here, and I which is running, j is fixed, jth component I try to find out, but this is the order of I is mismatched. In the just few minutes ago I show that for valid matrix multiplication the order is important, A I k B k j, this order one has to maintain in order to have a valid matrix multiplication. Here this is a vector components, these are the Tij is forming a matrix, when they multiply to each other, again this is a matrix kind of multiplication, but the order is not satisfying. In order to make this order change, I can do a trick, and the trick is that I put a transpose and then I put Tij. So whatever the value I have, if I make a transpose over that, then j and I will be interchanged, that I just showed before, and if I do that, then I have a expression where I have a valid matrix multiplication form. So eventually when I have these things, then T matrix, if T matrix is given to me, then my x vector in prime frame, the components of x vector in prime frame, x vector component, I should write component of vector x in prime frame can be represented by T transpose and x. This x is x vector in non prime frame or normal frame. So what I am getting, so let me conclude with that. So next day I will again come back to this issue. My E vector and E prime vector is related to a matrix like this. If my T vector is known, if I am able to find out my T vector, from that I can find the x vector, which is a given vector whose component, how this component is related to the previous component, this, utilizing the matrix T. So I know the T, I make it inverse, I know what is the component of x vector in non prime, I calculate that and I readily find out what is the thing in x prime. So I will show a very simple example with that. The problem, just me write down the problem, then today I am not going to solve that, I will going to solve that in the next class. The problem is one E1 vector is given natural basis this, E2 vector is given basis this, and prime basis is given like 1 by root over of 2 1 1. So I have two vectors in 2D, I have two vectors, basis vector like this, another basis vector like this. The problem is now a general vector x, which is say 2 5, can be represented as E 2 E1 plus 2 E2 5 E2. The problem is fill in the blanks. If I want to write in terms of E prime, what should be in the blanks? This is the problem, this is the definition of the problem. So, using this whatever I figure out here, using this treatment or this recipe, I will fill up this blank. What should be the value here? I will going to fill up. So, with that, so let us stop here because it will take some more time to calculate all these things and I need to discuss few other things also. So, with that, with this problem, with this definition, I will finish. In the next class, I will start with this problem, which is very important in understanding the transformation of basis. Very simple, in a very simple 2D structure. It can be done in 3D structure, 4D structure, in this structure, but the rule is that if E1 and E2 is related to a matrix T, if you know this matrix T, then using this matrix you can figure out your vector in E prime frame also, because this is known. For example, here 2 5 in non prime frame is known. What you do not know, that how to write this in the prime frame, where the prime frame is given by these two vectors, that we will do using this treatment. So, with that let me conclude here. So, see you in the next class, and then we will discuss all these things. In the next class also we will like to understand what is the transformation and what is the orthonormal transformation, what is called the similarity transformation. There are different kind of transformation that you can find with this formalism. So, that all these things we will discuss in our next class. With that, see you in the next class.